A very good evening, good afternoon, and good morning to all. I, Dr. Pallavi Saxena, SSC member of iLEAPS, and Dr. Samina, Project Administrator, iLEAPS, welcomes you all on the occasion of our iLEAPS Global Colloquium series, and it is our ninth talk in Global Colloquium series. So iLEAPS is Integrated Land and Atmosphere Interactions, which is a global research project of Future Earth. iLEAPS provides understanding of how interacting physical, chemical, and biological processes and transport and transform energy and matter through the land-atmosphere interface. So the prime purpose of this colloquium is to introduce the scientific society people with the distinguished and significant work of eminent scientists all over the world. So it is a very bright opportunity, especially for early career researchers, to interact with the distinguished speakers and establish the bridge between the ideas and knowledge through this platform. So for today's event, we have Professor Jana Sillmann, who is Professor and Chair, Climate Statistics and Climate Extremes, University of Hamburg, Germany. So she holds the Chair for Climate Statistics and Climate Extremes at University of Hamburg Research Unit for Sustainability and Climate Risk. She is also a senior scientist at the Center for International Climate Research in Oslo, Norway. Her research interests focus on relating physical and statistical aspects of climate extremes to socioeconomic impacts and risk assessment. She is using interdisciplinary approaches for better integration of natural and social sciences to support decision-making for mitigating and adapting to climate change. Professor Sillmann is lead author of Chapter 12, Climate Change Information for Regional Impact and for Risk Assessment in the 6th Assessment Report of IPCC Working Group 1. She is co-chair of Knowledge Action Network of Emergent Risk and Extreme Events, RISC-CAN. She represents the RISC-CAN in the Future Earth General Assembly. She is also co-leading activities of the World Climate Research Program, WCRP, Grand Challenge on Weather and Climate Extremes, and a member of the Scientific Steering Committee of the Integrated Research on Disaster Risk. So today she will be talking about the combining impacts of climate and air pollution on human health and agriculture productivity, and what are the challenges to assess the combined effect of these two on human health and crops, and opportunities for both fields to learn from each other. So I once again welcome Professor Jana. So Professor Jana, now the floor is all yours.
Yeah, thank you very much. First of all, for inviting me, and second of all, for this nice introduction. And I'm really happy to give a presentation in this iLEAPS Global Colloquium series. Now I share my screen. Do you see it?
Yeah, we can see that. Just.
And now do you see full screen?
Yeah, that's perfect. Yeah, perfect, Jana.
Okay, perfect. Okay, great. So yes, I promised to talk today about combining impacts of climate and air pollution on human health and agriculture productivity. This is joint work with my colleagues at Cicero, Christina Onan and Bob van Oort, and colleagues that I was working with in a different Research Council of Norway funded projects, and also European Union or from the European Commission funded projects, Exhaustion and SUSCRAP. So we have this century great challenges to cope with that regard issues around resource exploitation, environmental pollution, biodiversity loss, increasing populations that need to be fed, and on top of everything, climate change. And but there's also great ambitions this century in terms of dealing with these issues, and major landmark agreements have been signed by the United Nations in 2015, which concern the Paris Agreement to mitigate climate change, the Sustainable Development Goals, and the Sendai Framework for Disaster Risk Reduction. So we are in that context in big trouble, but also we have opportunities to face our problems. And I today focus on two of these problems, climate change and air pollution, which can interact to amplify the risk to human health and crop production. And this has significant implications for our ability to reach our sustainable development goals. For instance, if we want to reach zero hunger, good health and well-being for all, reduced inequalities, our climate change action, and for instance, life on land, and so on. So in my talk about the combining impact of climate and air pollution on human health and agricultural productivity, I will first address the connection between the SDGs and the Paris Agreement. I will talk about how complex systems need integrated approaches, and also I will explain how climate and air pollution interact. And I will in the talk highlight one paper that was a review on current methods to address climate and air pollution impacts on health and crops. And I will end my talk with some challenges and opportunities for further research. So you all know the Sustainable Development Goals, and we all know that we have climate change is acting now and everywhere. And with that, we have climate extremes increasing in their intensity and frequency. And that means that they can have negative consequences. For instance, to producing clean energy, because they affect renewable energy sources like wind power, hydropower is affected by drought, and then they can also affect our crop productivity by extreme heat, and so they affect our food security and so on. But also, if we think about achieving the Sustainable Development Goals, like for instance, improving health conditions, accessibility to good health care, if we reduce hunger and poverty, we also reduce the vulnerability to the effects or the impacts of climate change. And thus, by combining our aims for the sustainable development and climate change mitigation, we can have positive co-benefits. And just one example to show the interconnectivity between climate extremes in a complex system. Here on the example of the Russian heat wave in 2010. There we had the physical phenomenon of a long heat wave over Europe, affecting large parts of Central Europe and Russia. And these had negative effects, for instance, on the vegetation that suffered from drought and heat, that also led to forest fires. And this had impact on the crop productivity. We saw lots of crop failures, and we had a high air pollution due to the forest fires and also to the heat. That affected, of course, health, but not only the health was affected directly, but also crop productivity that affected wheat prices, and that indirectly can also lead to social instabilities. So with that also we saw in 2000 and also in 2003, these complex interaction of climate, air pollution, and socioeconomic consequences. We have to acknowledge that we live in a complex system and that everything is interlinked, and we need integrated approaches to address these systems. And just in a more conceptual way here to show, so climate extremes, if we don't mitigate climate change, we will see more intense and more frequent extremes that increase the risk for disasters. And this has, of course, impact on the agriculture forestry sector. And this, again, will affect our production of bioenergy and food production. But also the agriculture sector, for instance, has a role to play to mitigate a disaster or alleviate a disaster risk in terms of also impacting regional climate via for instance, we can affect the intensity of heat waves with changes in albedo, for instance, the agriculture, vegetation, forestry can also reduce disaster risk in terms of, for instance, avoiding landslides and so on and so on. So in order to address, for instance, the Sustainable Development Goals and the goals of the Sendai Framework for Disaster Risk Reduction, we have to see these systems in conjunction, and also and need to have a more comprehensive look on not only the impacts which are connected in terms of, for instance, impact on crops and health, but also on the drivers of those impacts, which can be climate and air pollution. So that's what we did, and that's why we did this comprehensive review in this environmental research letters topical review on combined impacts of climate and air pollution on human health and agricultural productivity. First, in this review, we elaborate on how climate and air pollution interact to then cause impacts. And so both climate and air pollution are driven by our, or climate change and air pollution are driven by our emissions. They come from industry, from cars, from transport, but also from agriculture sector. And these can be emissions of greenhouse gases that act in the atmosphere to increase climate change, but also they lead to air pollution, which can be ozone on the ground, and also particulate matter. These are small particles in the air that can be sulfide aerosols, black carbon, and other aerosols that are called air pollution. And these air pollution and also the climate change associated climate drivers like heavy precipitation, temperature changes in radiation, incoming radiation, or humidity can act as stressors for instance, the health sector, where we can see that humidity together with increased temperature can lead to premature death, cardiovascular diseases, respiratory illnesses, for instance, caused also by particulate matter, by these little aerosols in the air, and ozone, ground level ozone. But also agriculture, plants are affected by these climate drivers, and so air pollution and climate, like precipitation too much or too little, increased temperature can lead to reduced crop yields, crop biomass impacts, and crop quality in terms of nutrition. And so in terms of heat stress on human health, there's different levels, of course, of heat stress on human health. The first level, when temperatures exceed certain thresholds, is heat exhaustion, when people feel dizzy, have enhanced sweating, vomiting, and weak pulse. And if the temperatures rise even higher, They can be even lethal through a heat stroke, and when the body temperature rises above a certain threshold. And ground level ozone also affects the health. Via breathing, we take up ozone, and that leads to coughing, sore throat, shortness of breath, increased frequency of asthma attacks, and so on. And ozone, ground level ozone, you all probably know about the stratospheric ozone and think, oh yeah, ozone is actually good if it's in the upper level of the atmosphere, because it avoids dangerous incoming short wave radiation from the sun. So actually stratospheric ozone is good to protect us from skin cancer. But if it's developed on the ground, so we call it ground level ozone, where we live, where the crops are living, the ozone is generated by emissions that come from the industry, transport, agriculture, for instance, and it reacts with sunlight and can then cause destruction or impacts on our health or on plants. It can be taken up, but it also can be deposited. So we also see that there is a strong correlation between ground level ozone and surface temperature. So in this study by Lin et al., they have shown that the ozone anomalies here in gray and black on different locations are strongly correlated with the temperature anomaly over time. And also in this study with my colleague Noelia Otero, we have shown that the most important drivers for exceedances of health thresholds, the World Health Organization has put up some thresholds that should not be exceeded in order to avoid health impacts. And one of those thresholds is 50 ppb in summer. And so we see the main drivers over Central Europe, for instance, are the maximum temperature and the preceding amount of ground level ozone in the troposphere. So these temperature and ozone concentration are the primary driver of threshold exceedances for ozone impacts. But it's not only the health thresholds that are relevant, but also, of course, the plants take up ozone through their stomata. And these are little openings in the plant's leaf. And when we have ozone in the air and the plant is healthy and enough water is available, then the plants open the stomata and the ozone is taken up by the plant into the leaf, and then it causes damage to the leaves and the plant. If there's drought conditions, for instance, plants tend to close their stomata, so the ozone uptake is actually avoided, which is a good thing, so to avoid also damage. But a lot of our crops nowadays are irrigated, so we actually, with the irrigation, we support the uptake of ozone in the plants. And there's many other ways that particulate matter, which is another air pollution, and ozone can affect the plants. And in this paper that I said, we discuss several of them. And here I just highlight, for instance, the stomata effects that I just tried to explain a bit. But there's also, for instance, the temperature, the outside temperature and humidity affect how ozone is taken up by the stomata, and also the CO2. If there's a lot of CO2 in the atmosphere or increased CO2, it can lead to reduced uptake of ozone. And so there's these kind of interactions, but also on the on the plant itself. For instance, aerosols like particulate matter, like these little particles in the atmosphere, can avoid that incoming sunlight reaches the plant. So, and it affects the microclimate and will affect the biomass, and also the increased CO2 concentration in the air can reduce the biomass and yield. So there's lots of things going on where the air pollution and the climate variables interact and affect plants. So with that, I come back to the more conceptual level of how we address climate and air pollution impacts on health and crops together. So in order to, for instance, assess also future risk, and also to come up with effective adaptation, but also mitigation measures and policies. Because what we want to do is to avoid these kind of combined impacts by climate and air pollution. And so we need to consider them together. So in that kind of concept, we see the hazard is the air pollution and climate change. So we do have air pollution, ozone, and particulate matter that I consider in this presentation, for instance, and climate extremes, for instance, temperature extremes. And then to assess impacts and risk, we need also to be aware of the exposure. So where there is no plant or no person, there is of course no effect of the air pollutant or the climate, but also it's also for instance, heat and ozone exposure depends on a person being more outside or inside. It affects, like for instance, if we are in the growing season or outside the growing season. So this is part of the exposure. And then also the response of the crop or the human depends on the individual vulnerability or the ecosystem's vulnerability. So for instance, elderly people, young children are more affected by heat stress than a young adult, for instance, or people with health conditions are more affected by air pollution than healthy people, for instance. So the vulnerability plays a major factor that determines if we have impacts and how strong the impacts are on health and crops. And then if we have all these factors together, we can estimate the risk or damage of the combined hazards in the future. And that follows basically the concept of the IPCC risk framework, that risk is the interaction of the hazard, vulnerability, and exposure. Yes, and then of course in this talk I want to focus on what methods do actually exist to assess these impacts on health and crops, considering, for instance, the response and exposure and the combined hazard of air pollution and climate extremes. So I will discuss three common methods that we found in our review. So a large part of the studies we found use epidemiological or empirical studies that are also called exposure response functions that measure the response of a plant, for instance, or a human to a certain amount of air pollution or, for instance, temperature change. And that's often regression based or statistical functions. But they do look different. So here, for the health example, we have such exposure response functions, and they look, for instance, for the temperature like that. It's a often U-shaped form where we have this cold temperature on the left side, and then we have the optimum temperature, OT, reached at some point, and then we have an increase again with the heat extremes. So that's a U-shape for temperature. And for air pollution, these exposure response functions look different. It's not a U shape. We see that we have a sharp increase in the beginning of the, for instance, here particulate matter concentration, and then it flattens for even higher levels. So this makes it challenging to combine those response or exposure response functions for instance, temperature and air pollution. And here, these are examples for crops, exposure response function for crops. In that study, they have found, they have looked at crop yield here for corn, for different climate indicators, heat waves, hot days, maximum temperature, mean temperature, minimum temperature. And then you see, especially for the standardized climate indicator value, you see that there's not necessarily a linear relationship, but at some points we have a threshold where the behavior seems to change. So threshold exceedances are very important here as well. And then here is an example for the exposure response functions, and we for air pollution, which you see here again a linear relationship for different crops. For ozone impact on tomato yield or potato yield or wheat yield. Okay, so this is was the example of the 2D, but of course we want to look at the combined effect of climate and air pollution. So we actually need to go 3D. So we found also studies that you looked at epidemiological empirical 3D relationships, and these are often based on experimental studies, especially for crops. We can do experiments where we can expose the crop. Here you see open top chamber experiments that were conducted by colleagues at the Banaras Hindu University that were involved in a research project with us. And they did a long-term study to look at the combined effect of climate and air pollution on wheat, and they accounted also for different vulnerabilities by using different plant cultivars. So one was more adapted to heat and the other not, and then you could compare the different cultivars. Here you see the two types of wheat and the damages that the ozone has left on the leaves. So that's a way to look at the combined effect and also including different vulnerabilities in terms of, for instance, cultivars. In health studies, it's of course more difficult to do such kind of experimental studies to expose people to air pollution and heat. That is done separately. I mean, there are studies for air pollution where young adults, healthy adults are exposed to air pollution, and the experimental study is set up, or for instance, in the sports activities, they look at the effect of heat stress on the productivity, or yeah. But the combined effect of heat and air pollution, we have not found any experimental studies for health. But another point coming to health is also, if we think about experimental studies or looking at combined impacts, we have looked at many studies, not experimental studies, but where health studies looked at the effect of temperature that modifies the air pollution on impacts on health, or air pollution that modifies the temperature impacts on health. And so you can, of course, read all the details in the paper. What I just wanted to point out is that these kind of studies, they are very limited to a small range of study sites or areas. For here especially, we see highly developed countries where such studies are conducted. and not many countries in the global south, for instance. But different air pollutants were looked at in different health endpoints. So that points to in all these studies that we have found that there is a strong heterogeneity in these health studies, and it's really difficult to have a good overview or like a meta-analysis of the combined impacts of air pollution and climate on health. So what is then another method to look at the combined effects that can avoid these kind of localized studies and these very limited coverage in time and space, is that we use process-based modeling studies. And that's such process-based studies we know from climate modeling, for instance, and we also have global chemistry modeling. And we can combine, so with the two types of modeling, we can look at the chemistry climate interaction, also on very regional scales. For instance, what we did in one of the projects with the WRF chem model for India on a 15-kilometer spatial scale. And these can be combined with process-based or flux-based models that are applied in the ecosystem crop model research, crop research. For instance, with the DOSE model that looks at ozone stomata exchange. And so these kind of model approaches are much more advanced than the regression-based analysis and can cover larger areas. And some of the results from such process-based studies are also described in the paper. And here is one example from Tao et al., where they use climate models and scenarios to look at the climate change, ozone, and CO2 effect on wheat productivity. Another process-based model approach is also conducted by this AgMIP, the Agriculture Model Intercomparison and Improvement Project, which has long time focused on incorporating climate, crop, and agricultural economic modeling to look at future impacts on agriculture. But in a recent initiative, they also included ozone impacts. So they have now included models that can account for the ozone impact on crops, and then in the combination with, for instance, the CO2 fertilization effect and the climate effect. And also here, again, we have to see, I mean, a lot of these climate studies on crop yield have shown that CO2 fertilization can actually increase yield, but that could be counteracted by the ozone pollution. And also with climate change and more CO2 in the atmosphere, we also have more heat stress, which maybe the plants could still tolerate because we have cultivars that are more heat resistant. But people that work in agriculture productivity can be affected also by the heat. And especially where there's a low level of mechanizations in those countries, workers in agriculture production suffer from increased heat, and with that the agricultural productivity can also be reduced. And so there's this complex interaction between climate and pollution and development, which we have also looked at in another study with my colleague Anton Orlov. So just to sum up the different model approaches and applications that we have found in this review on human health and crop productivity. So as I said, we have these empirical regression-based studies, and this table you find also in the paper. And we see that on the right-hand side of the table, we see that for health, there are many studies using this empirical regression-based approach. But for agriculture, there are not so many studies that rely on that. For agriculture studies, there is more experimental studies that we found in the literature, but to assess the combined effect of temperature and air pollution, but nothing really for the health impact. And modeling studies, we find a lot of them in the agriculture sector based on semi-processed approaches or flux-based approaches, and also process-based, more advanced modeling studies. And there are only a few studies we found in the health literature. So the challenges using all these methods and different methods, which you have seen, is that there are effects that interact and are confounding. There's this confounding effect, like from temperature affecting air pollution affecting temperature, or for instance, health vulnerability aspects affecting impacts. These are very difficult to monitor, to quantify, to bring into these models. And then the data availability is an issue for many of these approaches. If we have only a few studies here and there, it's hard to do a more overarching meta-analysis to see the combined effect over a larger area or globally. And then also the model complexity is an issue. How much processes can we put into a model without increasing the uncertainties too much? Then we have seen issues with exposure response relationships, statistical relationships that often look different for air pollution or climate, and also they're affected by threshold tipping point behaviors that are difficult to quantify in this combined relationship. And then also we need to consider the system scales that we have in these studies. Some studies look at plants or human. Some studies look at populations or ecosystems. And so how can we upscale, downscale information we get from the different scales we look at? And then, of course, the spatial and temporal scales that we are able to address by having, for instance, fragmented experimental studies or limited data over time. So these are challenges, but there's also, of course, a lot of opportunities in terms of addressing these challenges. And one is, of course, we need to integrate more the effects of climate change and air pollution in order to develop effective adaptation and mitigation policies on a local, regional, and global scale. And for that, we could improve, for instance, health impact modeling by addressing more factors than are today considered. For instance, we could integrate aspects of demography, health status, activity level, indoor-outdoor time spent, and so on, in order to address more specifically the individual population and have more effective adaptation. It would be good to, in the impact modeling in terms of health, to go also to process-based modeling. And that can be supported by epidemiological, experimental, and clinical studies. But that's a long way. As I said, so far there's almost no process-based study available in the health sector. And for crop modeling, there's a lot of things going on in terms of process-based modeling and lots of interesting, exciting developments, as for instance in ACMIP. But one problem with the process-based models is also the evaluation. We need more empirical studies to evaluate our process-based models and inform process-based models. So more studies need to be done in order to provide data for evaluating and building our process-based models. And in terms of how, these empirical studies, we need more long-term and more large-scale experiments for human health and agriculture crops, especially in regions that are already warm and that are affected by heat extremes in the future much more than the north. For instance, Africa, India, and South Asia. And one, I want, in that context, I want to show you one, very relevant aspect. For instance, heat stress on human health. And here we looked in this study by Schwingshackel et al. We looked at apparent temperature and thresholds that are defined by health studies that lead to heat exhaustion, very high threshold, or heat stroke, extreme threshold. And you see that for a 3-degree global warming, we have in some regions, especially in the globe, around the tropics, we have exceedances of these thresholds where heat exhaustion occurs basically more than half of the year. And in terms of heat stroke, these regions are also affected by at least 2 months, 3 months in a row. So this is very critical if we look into the future, that these regions are affected by critical threshold exceedance in terms of heat. And then this information combination with this study from the same project, where heat-related mortality rate that can be attributed to climate change has been assessed. Basically, this study found that there is a 3-fold increase due to climate change of mortality. And but if you look especially at those regions where we saw that the heat stress or the heat increases the most, we have basically no data. And this outlines the issue of lack of data in critical regions where we actually urgently need more information to assess the impacts and the risk of climate change. And also, as I said, we need more knowledge on regional exceedances of critical thresholds or tipping points. And there are also great advances have been made since the last IPCC report, because in this IPCC report, we looked at changes in climatic impact drivers that affect different sectors and regions. And as you see on this very complex map, but we have assessed, for instance, heat, drought, mean precipitation, heavy precipitation, river flood, fire weather, and so on. And you see that every region on this planet is affected by different climatic impact drivers in the future. So no region, no sector is spared. And we also looked at different thresholds and threshold exceedances in the latest IPCC report, chapter 12 in the IPCR 6, and we looked at thresholds relevant for cities, for health, for ecosystem and agriculture. So I encourage you to look also in this chapter of the IPCC report. And here, this is one example from the technical summary, where we looked especially on the numbers of days exceeding critical thresholds in terms of heat warning index. We looked for different global warming levels, and we looked at how often this heat warning index that is also used by the US Meteorological Office, how often this is exceeded in different regions of the world. So here we have more and more knowledge that we can use, and but there needs to be, of course, much more done in order also to connect these critical thresholds or learn about critical thresholds from the different sectors in order to inform them by climate research and by also in air pollution studies. And this can be done or is done and should be done by joint initiatives across disciplines and communities. And for instance, one of these communities is Future Earth with their global research networks, which one of them is iLEAPS, and also their knowledge action networks. And one of those is the RISCAN, the Knowledge Action Network on Emergent Risk and Extreme Events. And this is a joint or supported jointly by Future Earth, the Integrated Research on Disaster Risk, the World Climate Research Program, and the World Weather Research Program. And so I think this is a way forward to address these complex questions that we have in order to understand better future impacts in the complex systems we live in. And with that, I want to close my talk, and I want to thank my contributors, but also the EU funded projects Exhaustion and SUSCAP, and also from the Research Council of Norway's supported project Sixpack. Thank you very much, and I welcome questions.
Thank you very much, Jana. That was such an exciting talk. And I'm just looking for some questions in the chat box. Attendees, you can write your questions in the question box and I'll read it. So I see one question from, let me see, there is a I can't Pallavi, can you read that question, please? Because mine is kind of stuck here.
Yes, sure.
Yeah.
The first question is from Saurabh Sonwani, and he's our ECR chair for South Asian and Middle East region. So his first question is, did you also, thanks Professor Jana for a very detailed talk. It was quite interesting that you have also worked in India. So the first question is, did you notice the impact of such stress parameters like temperature, ozone, and particulate matter on the grain size of wheat varieties? That's the first question.
Yeah, thank you very much for this question. And this type of research is done by the university in India, and they have seen effects on grain size as well. So it's not only the crop yield, but also the crop quality is affected. And I welcome you to look at the Sixpack website in basically at Cicero. I can put it in the chat or so, because there we have also a report where we did 2 workshops in Asia, in India and Nepal. And the last one is a policy recommendation document. And there we have basically summarized what we found in our studies and in India and Nepal in the Indo-Gangetic plain on also impacts on grain and yeah, food quality. Yes.
The second question is connected to that. Apart from analyzing the impact of different stresses on wheat variety in India, did you also identify the impact of such stress on rice variety in India, as rice is also an important crop of many countries?
We have not looked at rice in our detailed study in the Sixpack project or in the SUSCAP project, but there are, of course, studies which I have not done in that sense. But we have, if you look at the paper, there is an extensive literature where you can also find impacts on rice, or studies on impacts on rice.
Thanks, Professor Jana. The second question is from Dr. Silvano Fairs. He's our SSC member. Thanks for the nice talk. Do you foresee potential of using artificial intelligence application to resolve confounding and interactive effects of pollution and climate change?
Yes, I think this would be, I mean, we need to use more and more of these advanced statistical methods. I agree, but all statistical methods depend on data. So there is a trade-off in terms of how much we can apply new statistical methods if we don't have sufficient data, but also maybe we can address data gaps with artificial intelligence and also maybe complement climate data, experimental data with remote sensing. So there's more and more opportunities the more data we collect with different types of tools and then how we analyze it. So definitely this should be more exploited.
Thanks, Professor Jana. The next question is from Dr. Vanessa Surepepal. She's asking, is there a joint index to quantify and let the public be informed about the impacts of air pollution and climate change to both health and crop, anywhere available or applicable?
A combined indicator is not available to my knowledge, especially not combined for crop and agriculture, because we have to be, even if there was a combined ozone and heat index, that would be of course possible, because we have, for instance, the World Health Organization thresholds for critical ozone levels, and we have the health critical levels for heat stress. So we could kind of combine that in a compound event manner. So this would be possible. But in terms of impacts then on crop or health, I mean, there's different thresholds for humans and different thresholds for agriculture, and especially different thresholds for rice or wheat, or so that indicator would then need to be informed by the different exposure and vulnerabilities from either health or agriculture, if you're interested in elderly person, or in terms of crop in wheat or the different plants. So it's that is really individual in that sense. So I think a general index cannot tell you the whole story.
Thanks. The next question is from Professor Ramesh Singh from Chapman University. Do you think pollution impacts crop productivity?
Yes, pollution impacts crop productivity. Yes, because in various ways that I had tried to illustrate, maybe it was a bit a complex figure, but there is the pollution affects via plant uptake. It affects basically the leaves. It affects the biomass. It affects the grain size. Pollution is also in the air, affects the incoming radiation, so it affects again the growing. So pollution in terms of aerosols, pollution in terms of ozone can affect crop yield in many ways, and there's a lot of studies on that aspect only that can be found in the paper, in the review paper I outlined. So there's lots of literature cited there that look at the pollution impact on crops.
Thanks. I'm not able to see any of more questions. Samina, do you have a question from your side?
No more questions on here. Jana, can I ask a question? It's going to be more political, because because you said based on your result in Asia over India and Nepal, you came up with some recommendations with the policymakers. So if that is not confidential, can you share? Because is it about changing the crop, or introducing more seasonal crops, or the pattern? Or what was it? I'm just a bit curious about that recommendations.
Yeah, so there's a whole report also illustrated with some policy guidance as a conceptual figure. So it needs to be a combination of methods. It cannot, I mean, one thing is the technological improvement of crop productivity in terms of having more resilient cultivars, for instance, or basically improving the plant and improving, for instance, how we produce plants. Like we can use different irrigation patterns. We can, yeah, there's lots of things that we can technically do, but there's also, with one study in Nepal, we found that we did interviews in Nepal, and we found that basically the farmers, they are not so much concerned. I mean, they don't even know about the air pollution effect. So there needs to be much more education amongst the farmers that there is also air pollution, not only climate that affects the plants. Because they realized in Nepal, they have health consequences. They have a hard time to breathe, but they didn't know that it also affects the plant. So there needs to be education and information, and then of course also policy action in terms of reducing air pollution. And so there's, and also to consider the societal context. That was also one recommendation or one study we had, because in Nepal, the farmers concerned with climate change, there's this restructuring of the agriculture to address climate change, but maybe that is not in line with the reality that the farmers live in, and so there's some of those contextual information that needs to be taken into account in order to design effective policy measures. So that was also one of the recommendations. Yeah.
Okay, thank you.
Professor Jana, I have one question. If we talk about the sustainable cities, then according to you, what are the policies or measures do you recommend that is with integration with air pollution and climate change?
Yeah, sustainable cities, I think there's lots of opportunities there if we keep these different aspects in mind. For instance, of course, we can, I mean, in cities, we also have now the additional effect of urban heat islands, so we have even more heat stress. And we could counteract, of course, with air pollution, air conditioning. But then we increase our emissions with that if we have fossil fuel driven energy sources for air conditioning. But we can have lots of nature-based solutions, for instance, greening the cities, having less concrete, and having less traffic, more public traffic with electric vehicles, so we reduce air pollution again. And so seeing the city as a system that has many problems, but also many opportunities to basically for co-benefits in terms of one aspect, reducing also another aspect, and this helping to improve health conditions, or for instance these kind of farming on the rooftops, or in small scale farming, or there's all these new innovations that can be done in sustainable cities. So, but the thing is that we need to keep in mind that things are connected, that we have not only one hazard but many hazards, and that sectors are connected, and that we have more the complexity in mind when we try to solve or design a sustainable city. So have all actors at one table discussing the challenge and then coming up with the joint solution.
Thank you so much.